Hello, my name is Tyler Dollywell, and today I'll be trying to explain to you light refractivity with respect to the horizon problem. In 1963, Charles Milner identified a problem with the standard cosmological model of the Big Bang, whereby different regions of the universe, however separate they are, exhibit isotropicity. This is notably with respect to temperature measurements of the cosmic microwave background radiation, CMB, whereby the temperature at any point in the universe is a constant 2.782 Kelvin. Now, the logical question that arises from this, especially with respect to this graph, which I'll get to in just a second, is how on earth is this isotropicity possible? So we're going to look at this graph where on the y-axis we have the radius of the universe, and on the x-axis we have the time in which the universe existed. And while the slopes here are identical from here and here to here and here, at the 10 to the negative 37 second mark, at the 10 to the negative 35 second mark, specifically this dashed interval right here, we undergo a rapid period of superluminal expansion noted as the inflationary theory by Alan Guth. And this superluminal expansion is peculiar because you have this rapid expansion universe where different density fluctuations are dispersed at great distances from each other. Yet once they develop into matter, they have the same temperature, same properties as each other without communication, as it seems. Because if the maximum rate of info transfer is the speed of light, how can they communicate with each other if the speed of light is, as it is today, 2.9979 times 10 to the power of 8 meters per second? A rather trivial velocity calculation, velocity equals distance over time, would reveal that the speed of light necessary to facilitate said communication and maintain this isotropicity would be to a magnitude of 10 to the 33 meters per second, which is far greater than the speed of light today. So two solutions that were proposed as of today, they're rather notable. Alan Guth introduced cosmic inflation, which is what I talked about just then. It only reduces anisotropy, so it doesn't talk about the speed of light. It completely ignores the fact that the speed of light could vary, and it takes into account the fact that just because everything is so compact, he states that because it expands so quickly, the properties don't change. So it only reduces anisotropies. But what's really the main flaw in this model is the fact that the entropy before the thermal expansion is greater than the entropy after. And that's problematic because entropy typically increases with increased volume. More recently, theories about variable speed of light, variable celerities, have arisen. And what's particularly notable about these theories is that they eliminate anisotropies completely, because if we could have light travel at 10 to the 33 meters per second as outlined in this inflationary period before, there wouldn't be a problem. The isotropicities that we noticed before, the temperature being a constant 2.782 Kelvin, would make sense. However, it obviously deviates from the fine structure constant and Lorentz invariance. These two terms are scientific jargon, but what they relate to is special relativity. And in the gist of this is, if you vary the speed of light, you're deviating from special relativity, which has a lot of empirical evidence supporting it, and so that's why it seems very unlikely. So now we move on to the critical geometry of the thermal Big Bang. This is just all this fancy math here. To be honest with you, I don't understand at all. You just notice a heavy emphasis on density, as underlined by green. So these density fluctuations are the seeds of the universe, and their influence there's a lot of influence they bear upon the spectral index and S of the universe. And the spectral index of the universe is gauged on a bimetric scalar tensor model, whereby the speed of gravity is, with respect to inflation theory, not constant, whereas the speed of light is, and with respect to the variable speed of light theory, the speed of light is not constant, whereas the speed of gravity is. Now, with respect to the former, we have an NS of about 0.96478. That's a recently calculated value, and that gives us a testable prediction. So the Planck satellite, which is orbiting the universe as we speak, or traveling through the universe rather as we speak, is going to find a value for us eventually of the spectral index of the universe. And if that is 0.96478, that provides tantamount evidence proving the cosmic inflation theory. What's important to note about this bimetric scalar tensor model is that the NS value for both cases is quite similar. We have an NS of 0.96478 for the inflation theory, and we have an NS of about 0.965 for the variable speed of light theory. And what this NS is if we look at this proportionality over here, the radiated flux density is the rate at which information can be transferred between two media. It's going to be proportional to the velocity to the power of ns, assuming that ns is less than 1. And because NS is so great, we get a proportionality where the radiated flux density is directly proportional to frequency, and accordingly, there's a similar rate of energy transfer between both models. So both models rely upon a high rate of energy transfer to mitigate anisotropy. However, it is specific emphasis of this video is the variable speed of light theory, only because there have been recent studies as of November 25th, which provide interesting results about said theory. So we're going to look at possible solutions. The first one being tachyons, which are just particles which are thought to be able to travel faster than the speed of light. However, because of the relativity of simultaneity exhibited by the tachyonic antitelephone, as illustrated by this equation below, it violates causality. As in inertial frames of reference, you can't have something happen in two different places at the same time. That would imply time travel, traveling back in time, and with regards to causality, that's just not possible. Then we're going to look at virtual photons as provided by Richard Feynman. They lie in dimensions of Heisenberg's uncertainty principle, so no definition of velocity can have meaning with respect to motion. And what that means is, no matter how you manipulate these virtual photons, they cannot transfer energy faster than the speed of light. So the two most interesting theories are already debunked. Now we're going to move on to perhaps the most promising or most commonly misconceived solution about the FSL, about varying speed of light theory, and that is speed of light can vary in different media, which is true, however, it's often misconceived. So we're going to move on to the experiment now, and then we're going to talk about this. So right now I'm shining the laser beam through the glass containing water. So the main boundary to note here is air to glass, glass to water, water to glass, and then glass to air. And you'll notice a slight bend, or you might not notice because it's going to be rather small, bend in the light beam. Now we're going to move on to the glass containing just air. And now we'll move on to the glass containing olive oil, all of which have different densities. So there's our experiment. So in explaining the misconception, we have to note that there's a difference between the phase velocity of that beam and the signal velocity of that beam. The signal velocity is what carries the information. That's what would carry the heat or energy that would link the universe together, that would mitigate, which would cause that isotropicity. So the signal velocity is always, no matter what medium you put it through, always going to be 2.9979 times 10 to the power of 8 meters per second. But the phase velocity, we can slow down to 2 miles per hour, we can speed up to 10 to the power of 15 meters per second. And that's because, if we look at these diagrams down here, in a vacuum, we're going to have 3 different waveforms. So in a vacuum, this is our waveform 1 of amplitude this, and the prevailing edge here. The prevailing edge is the signal velocity, and the distance between the arrow here and the waveform rather, is the velocity. In a medium where density is greater than 1, we have a slightly greater wavelength, but the prevailing edge is still the same place. And in an anomalous dispersion, we have the, you notice a great reduction in the wavelength, an increase in amplitude. However, you still have the prevailing edge at the same place. That prevailing edge is what delivers the news, the information. That's still 2.9979 times 10 to the power of 8 meters per second. However, this pulse, right here, this light pulse, can be measured at varying speeds. And a couple key notes to make here are that during refraction, frequency remains constant because the oscillating electric magnetic fields on either boundary must be equal. This is exemplified in 2 cases. If you look at the string here, which is thinner on one section and thicker on the other, frequency is constant because the strings are joined, however, and because energy must be conserved, but the wavelength is not constant because it changes in the permittivity or permeability of the medium. As explained by these calculations down here below, whereas permittivity is equal to 1 over velocity squared, so velocity changes, and if velocity changes and frequency is constant, then lambda must change. And this is all summarized in this diagram down here, where you have your magnetic field, your electric field, and your velocity. And you notice how on either side of the boundary they are equal, which further ramifies the notion that frequency remains constant. And a couple interesting consequences of this is that color is dictated by frequency and not wavelength. As you may have noticed when we were doing the experiment, the color of the beam of the laser beam did not change, it remained red throughout. Not even a change in the shade of red, it was the same throughout because the wavelength was changing but not the frequency. So with respect to the Big Bang itself, it seems like we haven't come up with a solution here at all. We haven't. I'm just a first-year university student with barely any knowledge of what I've spoken of on the board. Like, until I have an understanding of what this means, I won't be able to provide you with a potential theory resolving the problems of the inflationary theory. My leading thought is we have to look at tachyons in a non-inertial frame of reference where this causality can be violated.